Me okay, Stephanie? Mhm. Oh, good. Thanks for letting me know you can hear me. Okay, this is Paul Geyer, and I will be the presenter today for this webinar, Ethical Issues. Hang on a sec, from the Tacoma Narrows Bridge collapse. Um, First of all, let me mention that I don't use this Zoom system very much for meetings. And so I've kind of been fumbling around here getting organized. I assume that you can all hear me on the audio and see my slides. I can't, for whatever reason, hear you on the audio. So if you have a question or a comment, use the question and answers box, and I'll try to keep an eye on that as we move along. The way these webinars move forward here is I press on with the presentation for 50 minutes, then we take a 10-minute break. um, then uh, we go for another 50 minutes, and that concludes the webinar. However, we'll take about the last 15 minutes of our time to uh, provide an opportunity for any of you to offer comments or ask questions, and then we will go through the quiz quickly. This is not obviously a highly technical at all presentation, so the quiz is pretty easy to deal with. Okay, ethical issues from the Tacoma Narrows Bridge collapse. Now, usually the way I do this webinar is I uh, go through the body of the presentation, and then as we move through that, I will highlight, here's an ethical issue that popped up, and then here's another one. I think what I'll do now is just tell you right here at the start, there are two ethical issues that I believe this story illustrates. The first one, and I'm just stating this in a very succinct uh, manner, but the first ethical issue is don't compete for engineering design work based on price or upon uh, comments or that you might make about how you can do the job faster, quicker, deliver a better quality product. Don't compete for engineering work on that basis. Now this will hopefully become clear to you as we press through this presentation. The second ethical issue that I believe this story raises and illustrates is that you need to make sure that you have enough experiential knowledge to undertake the project that you've got. Theoretical knowledge is not adequate. In the business that we are in, which you might say is the infrastructure business. It's all what we do is the designs that we produce should almost, in my view, always be based upon experiential knowledge. In other words, how has this been done in the past? Did it work? Let's try the same thing here. Uh, you can, if your experiential knowledge doesn't cover um, uh, uh, all of the area that you're dealing with, yes, I think you can take some little baby steps outside the body of your experiential knowledge, just using uh, theoretical knowledge, some calculations that one of our academic friends came up with and published. But those are the two issues. Don't compete for engineering work based on price or claims that you can complete the work faster, cheaper, better quality. And secondly, in the business that we're in, we have to be very sure that we have enough experiential knowledge to complete the project successfully. And so I hope this will become clear as we push through this. Okay, let's see. Learning objectives, et cetera, et cetera. You can review this at your leisure. I think that you get a copy of these PowerPoints um, from Hisham, and so you can review these at your leisure. Now here's what I'll be talking about, kind of the way we'll walk through this chat. First of all, I'm going to give you quite a bit about the history of this project, because it's because of the history of the project that the ethical issues arose. This will hopefully be clearer again as I move forward. We'll look at the design proposals for this particular bridge, the Tacoma Narrows Bridge. The uh, the problem with the bridge uh, cropped up while it was still under construction, before it was ever completed. And the big indicator that something was wrong is the bridge started to oscillate. There were some Band-Aid type measures that were applied to the bridge to try and mitigate this oscillation. And then on a particular day, the oscillations increased greatly and the bridge collapsed. Then there was an investigation, and it was during the investigation of the collapse that I think the ethical issues were very important. And what did we learn? We as an engineering profession learn as a result of the failure of this bridge. I think that the profession learned because we have not had similar failures, at least very few of them, since this incident took place. Now, this took place back in, let me see, I've got a question here in the chat. Please use Q&A for Q&A. And okay, that's just Hisham's comment. So, and then after the bridge collapsed, what was done? Well, a replacement bridge was constructed, and it's up there doing a very serviceable job today. So let's the ethical issues, I kind of already told you what I think the focus of the ethical issues are, is the the distinction between theoretical knowledge and experiential knowledge. Theoretical knowledge is someone sits down, perhaps someone in the academic community, comes up with some calculations based upon a theory that he or she has about how things work. And then, but that's a theory, and that's all it is. But then there is the experiential knowledge. How were bridges of this type and in this situation designed and constructed in the past? Did they work? Okay, let's design this bridge based upon that experiential knowledge. And then the second ethical issue is the commercial interests that may influence or force design schemes or proposals. The everybody involved in the infrastructure business, either on the design side or the construction side, is under frankly very significant economic pressures to get the job done and keep your bank account in one piece. So the economic forces that you have to be aware that they can and they do arise, and to not let those influence decisions that are made. Just by way of, I guess, introduction, this is me, and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight ahead designer, designing very large projects, all the way down to little small ones. For 18 years, or 17 years actually, I was with a large public agency, the state of California. And for the first 10 of those years, I was engaged along with a couple thousand other engineers in the design of one of the two things that I have been told an astronaut can see from outer space. The first of those two things is the Great Wall of China, and I did not work on that one. The second one is the California Water Project, which is a 500-mile long collection of dams, reservoirs, power plants, pumping plants, every conceivable kind of hydraulic structure that moves water from Northern California, which is where you get the rain, and you got water, a lot of water in Northern California. Southern California, you don't have any water. Particularly the focus, of course, is Los Angeles. And Los Angeles has fabulous weather and great beaches, but no water. It's a natural desert. And so the California State Water Project was moving water from Northern California down through Central California to Southern California, the Los Angeles area, and where it's utilized. After that adventure, then I moved to another department of the state of California where the projects were small to medium size. So this is kind of, I'm giving you this exciting background because so you can get a picture that I've had a bit of exposure to different kinds of projects for across the whole spectrum of size. Then after that 17 years I resigned, started my own engineering business for 18 years. I was providing contract engineering and architectural services for largely, but not exclusively, public agencies, particularly the military. And the projects there were in the small to medium size range. And after that, 18-year adventure for an additional 9 years, I was a principal staff advisor to the California legislature on infrastructure and capital outlay issues. So out of the drawing board design business and in what might be characterized as the public policy arena. Okay, the Tacoma Narrows Bridge. The the bridge that we were talking about is in Washington State, up there in the upper left-hand corner, sometimes referred to as the coffin corner of the United States. Uh, I hope none of you are from Washington State. Um, the Tacoma Narrows Bridge. And what we're talking about here is the original Tacoma Narrows Bridge. And this incident, the bridge was designed and built and collapsed back through the late 1930s into the early 1940s when it collapsed. Subsequently, after World War II, there was steel became once more available on the market, which it was not during World War II because it was all being used for the wars in Europe and in the Pacific. And so the steel became available. So in, I think it was 1946, the replacement bridge was designed, constructed, and it's up there in Washington State doing a very nice job. And the bridge was designed to cross a body of water called the Tacoma Narrows, which is part of what's called Puget Sound. You've probably heard of that, which is kind of the bay, if you will, that serves primarily Seattle, but also Tacoma and Olympia are a couple of other cities that are up there. And this is a kind of an unusual bay in that it's and you'll see a picture of it here. It's a lot of channels in it. It's not a big open bay. It's like a can of spaghetti. And this bridge was constructed to cross a part of the Puget Sound, the part called the Tacoma Narrows. And the bridge was constructed between the city of Tacoma and an undeveloped area called the Kitsap Peninsula or the Olympic Peninsula. This bridge was at the time the third longest suspension bridge in the world. Construction was completed in 1940, in July of 1940, and in November of the same year, 1940, it collapsed. Let's see, I've got an indicator here that there's a chat message. Okay, Joseph said he had a problem connecting to Zoom, but he's connected now. So anyway, this is what we're talking about. And again, this is going to sound like, a history lesson or something like that. But I believe that it is very relevant that you, as far as this incident, this collapse of this bridge, that you understand the history of it, because it was the history that drove the unfortunate decisions that were made that led to the collapse. So here you see an aerial view of part of Puget Sound. You see the city of Seattle up there on the upper right-hand side. And then you see the city of Tacoma there, and then you see the red arrow, which is pointing to the waterway, the Tacoma Narrows, and the bridge was across that uh, body of water, that channel. And you also see on this some things highlighted that you're probably wondering what they're doing there. But the Bremerton Navy Yard, McChord Airfield, and Fort Lewis. Um, Bremerton Navy Yard was then and is now one of the most important Navy facilities, military facilities on the Pacific coast. And at the time of this incident, there was a facility called the McChord Airfield. At that time, in the late 30s and early 40s, there was no Air Force. The airplanes belonged to the Army. So there was something called the Army McChord Airfield down at Tacoma. And then a little further south, getting down towards Olympia, the state capital, was an Army base called Fort Lewis. And the fundamental purpose of McChord Airfield and Fort Lewis was to protect the Bremerton Navy Yard. And this was important in the late 1930s and the 1940s because of World War II and the threat of attacks from the Japanese in the Pacific. And Bremerton Navy Yard would have been a prime target for Japanese because next to, on the Pacific coast, next to San Diego, it's probably the most important naval facility on the Pacific coast. And protecting it were McChord Airfield, the airplanes, and Fort Lewis, the Army. The problem was the distance between McChord and Fort Lewis and Bremerton. And let me, okay, here are some numbers that give you a picture of, for instance, how long it would take to get from Olympia to different places on the Kitsap and Olympic Peninsula. And because of all of these waterways there in Puget Sound, to get before the construction of this bridge, before you could get from Tacoma, where Fort Lewis and McChord more or less were located, to a place called Gig Harbor, which is up on the Olympic Peninsula. Driving around all of these channels would be 107 miles of driving. But if there were a bridge across the Tacoma Narrows, the distance would only be 8 miles. So the driving time would change from 2 hours and 10 minutes to about 17 minutes. Specifically from Bremerton to McChord, if you had to drive around without the bridge in place, that would be 79 miles versus 39 miles if there were a bridge. So the driving time would be reduced from an hour and 50 minutes to 55 minutes. Now, and then there are some other illustrations here to other points on the Olympic Peninsula, which again, this was considered by the military to be the prime objective of Japanese military forces during World War II. Now, these improvements as a result of putting in the bid don't sound like a big deal. Driving time reduced from an hour and 50 minutes to 55 minutes. And in the normal everyday commercial activities, that isn't a big reduction and not all that important. But from a military standpoint, it was very important. And all you have to do is just think a little bit about Pearl Harbor and the importance of time at Pearl Harbor and what happened, when there was um, not enough time to get prepared. So um, the this is the picture of a reason why the bridge was constructed. Here, just to put things in context, is an aerial photo of the Tacoma Narrows Bridge today. Um, now, the off on the left-hand side there is something that, to my eye, looks like an abandoned military airfield, uh, of, uh, most likely of World War II vintage, and those are all over the Pacific coast here, and they've been turned to civilian uses. And anyway, you can see that Fort Lewis and uh, McCord are on the right side of the waterway, and this airfield is on the other side of the waterway. So it's just you could protect it from a military standpoint uh, uh, quite well with if you had a bridge to get across the Tacoma Narrows. But the bridge at that time, and that time we're talking about, is the late 30s, 1940s. So again, more history. And again, the reason for going through this history is to uh, show how the ethical issues arose, which led to the collapse of the bridge. So the bridge, the idea for a bridge first popped up back in the 1880s. Now the Olympic Peninsula is a real treasure trove of trees, lumber. Lumber has always been a huge economic factor in the Pacific Northwest. And so there are all of these trees in the Olympic Peninsula, and but there was no way to conveniently get the lumber out of the peninsula to the sawmills, which tended to be around Olympia and Tacoma and further south. And in the 1880s, of course, no automobiles, no trucks. And so the only way essentially to get the lumber out was by rail. And the dominant railroad in the Pacific Northwest at that time was the Northern Pacific. And the railroad saw that if they had a bridge across the Tacoma Narrows, it would greatly shorten the distance they had to go to pick up the lumber and take it down south to the lumber mills. And so in the 1880s, the Northern Pacific began to agitate, if you will, to get a bridge constructed. But the Northern Pacific Railroad wanted a low-level bridge, a causeway type of bridge. And they wanted that because it was cheapest. And also, railroads don't do well, don't do well on grades. So a high level bridge, such as a suspension bridge or a cantilever bridge, a cable stayed, um, is not something that would work for a railroad. So the end result is that although the Northern Pacific wanted to get a bridge constructed, it was unable to do so. And also another major impediment for constructing a causeway type bridge was that in the 1800s, the federal government recognized that all of the waterways here in the United States, the Mississippi Basin, et cetera, et cetera, et cetera, the Pacific coast, that all of these waterways, rivers, were a very important transportation asset because back in the 1880s, uh, uh, commercial transportation was via uh, canals and rivers and things like that. And so the federal government recognizing that it would destroy these convenient waterway trails if you were to allow the construction of low-level causeway type bridges. And so the federal government decreed that you could not construct a bridge that would impede a navigable waterway. And boom, there went the Northern Pacific's pipe dream. And so the Northern Pacific, a railroad bridge, was not practicable. Moving through time, we get into the early to mid 20th century, 1920s. And at that point in time, the Pacific Northwest was developing more and more. And the cities of Seattle and Olympia and Tacoma were developing. And the business and government interests were interested in having a bridge across the Tacoma Narrows for their commercial purposes to get between Olympia and Seattle and Tacoma and Seattle. And so in the 1920s, commercial interests began to agitate for a bridge across the Tacoma Narrows. And the city had some bridge engineers draw up some schemes to use for them to use to try and get the financing for a bridge. Here is one of the schemes that proposed for the Tacoma Narrows, a suspension bridge. It would be high enough to avoid impeding the navigable waterway. And let's see, hang on a second. I've got a leaf blower outside my window. I'm going to put some shutters down. Hang on for just a minute. Okay, I think I may have gotten rid of that noise. Um, so here was a proposal, nice, attractive bridge, and no money to build it with. Here was another scheme that was proposed, a cantilever bridge. This was drawn up by the Tacoma City engineer. Design but no money to build it with. And so no money to build a highway bridge across the Tacoma Narrows, impractical to design a low-level railroad bridge. And so uh, the commercial and business interests in the region and the state of Washington government began looking around for other ways to possibly finance the construction of the bridge. And so, one scheme that was uh, explored was to use tolls to construct a toll bridge, and then uh, people would pay, obviously, to use the bridge. Nice idea, but uh, the demand for automobile traffic up there in that area at that time in history was very limited. So the amount of traffic that was uh, uh, possible to just wasn't there to fund the construction of a toll bridge. And so that didn't pan out. So the state of Washington said, well, let's at least put in a ferry system so that people can get from one side of the Tacoma Narrows to the other side by putting their car on a ferry, and the ferry would take them back and forth. And so the state of Washington um, entered into a contract with a private company to run a ferry service across the Tacoma Narrows. But included in their contract with the private company was a provision that there would be no competition for the ferry companies. So they couldn't let out, the state of Washington could not let out another franchise for a ferry service in competition for this one that they originally signed with. And uh, uh, so there was a no compete clause in there, and that no compete clause uh, also covered the construction of a bridge. And so if you were to construct a bridge, that would be in competition with the ferry line, and that was not allowed. So things were looking pretty grim in the late 20s and early 1930s. Um, but then, as you moved into the 1930s, the specter of World War II began to appear on the horizon. And the importance of the Bremerton shipyard was very clear to the politicians in Washington, and the importance of McChord and Fort Lewis to protect Bremerton was also quite clear. So the federal government began to take an interest in providing funding for the construction of a bridge. And the along with the specter of World War II coming on the horizon, this was the 1930s. And of course, as we know from our history books, uh, the country, the US, was in a deep depression during this period. And the federal government, the Roosevelt administration, believed that an important tool to get the country out of the Depression was federal funding of public works projects. And so the federal government began to provide a great deal for infrastructure projects all over the U.S. And as an economic stimulus activity. And so a bridge like this Tacoma Narrows bridge that was proposed fit nicely into both of these categories. It would fill an important military objective, and it would fulfill an economic stimulus need as perceived by Washington. So now the um, bridge begins to look more feasible from the standpoint of getting funding, and the military necessity and the economic stimulus necessity, if you will. And so the Washington State Department of Highways, uh, the government agency, put together a proposal for the construction of the Tacoma Narrows Bridge and requested $11 million from the federal agency that held the purse strings, which was something called the Public Works Administration. And so Washington submitted a proposal, a request for $11 million. Now, remember, we're talking about the late 1930s, early 40s. So obviously, you wouldn't build $11 million today. So the Washington State, the public agency that was cobbled together was something called the State Toll Bridge Authority, and the engineer who took the lead in proposing a design to the federal government was a gentleman named Clark Eldridge. He was the project engineer on the Tacoma Narrows Bridge proposal as proposed by the state of Washington. And an aside that has nothing to do with this story, but it's an interesting little vignette. The director of the Washington State Highway Department at that time was a gentleman named Lacey Murrow, who was the brother of the very famous and well-known newscaster Edward R. Murrow, all through the 40s and 50s and into the 60s. Again, this has nothing to do with anything, but it's an interesting little sidelight. So this was the proposal that the state of Washington under Clark Eldridge proposed: a suspension bridge with road support girders that were reflective of the experiential knowledge, if you will, at that time about how to design suspension bridges, and in particular the roadway support girders. And to get the necessary strength, uh, the the experiential knowledge at that point in time said that the roadway support girders should be open truss girders. And the truss girders proposed by Clark Eldridge were 25 feet deep, which was like I say, was reflective of the experiential knowledge at the point in time. There were bridges that had been designed with deep, open truss roadway support girders, and they were all working just fine. So this was the proposal by the state of Washington. Um, Now, this is when economics and commercialism creeps into the picture. Uh, the There's always been a pushing and shoving that's gone on major public works projects, whether they should be designed in-house by government engineers or should they be contracted out by engineers. And so the private engineering community, particularly a group of uh, private consulting engineers on the East Coast that were uh, led by a prominent bridge engineer, Leon, who was very well known and had a great deal of credibility at that time. And these private engineers undertook to convince uh, the government bureaucrats in Washington who controlled the purse strings to contract out the design of the bridge to them and to convince uh, the federal bureaucrats to contract out the design of the bridge or to mandate that the state of Washington contract out the design of the bridge. Moiseev and his associates submitted a design which was had substantially shallower roadway support girders. They were of an I-beam configuration, and they were not open web girders. They were solid plate steel, and they were only 8 feet deep. Um, so you've got two design concepts on paper. One submitted by state of Washington engineers, uh, used a conventional 25-foot deep truss girders to support the roadway structure, to support the roadway. And the other competing design was a solid I-beam configuration, girders only 8 feet deep. And Moiseev said that we can, if you contract out this design to us, private engineers, we can do it for only 6.4 million as compared to the 11 million proposed by the Washington State engineers. So the federal, I don't want to call them bean counters, but the people that controlled the money in Washington looked at this and said, wow, we can save the taxpayers a lot of money here by contracting out the design of this bridge to private engineers rather than to provide to the Washington State Department of Highways engineers. And so that was what the federal agency mandated the state of Washington do. Put this design contract out to private engineers because they can do it a lot faster, cheaper, better, purportedly. Now, Uh, the state engineers with the state of Washington, of course, were, you might say, upset by this competition from these private engineers. And the state of Washington, uh, in addition to its in-house engineers, hired um, expert bridge designers to evaluate Moiseyev's plan, and it was determined to be, quote, fundamentally unsound. Uh, it was indicated that the design made the Narrows Bridge lighter and narrower than any built, and this was done in the interests, quote, of economy and cheapness. Um, so here is Mr. Moiseyev, who was leading the private engineering group. And this was the proposal that Moiseyev and his associates submitted. It was a suspension bridge, but the big distinction was that the roadway support girders would only be 8 feet deep instead of 25 feet deep, and they would be of a solid I-beam configuration. Uh, and an important point that this incident really illuminated was that with open truss girders, the wind passes right through the girders. With an I-beam configuration, wind does not pass through the I-beam girders. And they they are just functioning as kind of a sail, if you will. Okay, so this was Moiseyev's design. He said, I can do it for 6.4 million. State of Washington's design with those big deep truss girders going to cost you 11 million. Give the mandate that the design job be given to us private engineers, and we can save you a lot of money. And the federal government bought that. Now, Moiseyev relied in his design on a theory of bridge design that had been published in a reputable engineering journal put out by ASCE, and it represented a deflection theory developed by a gentleman, an Austrian engineer. And essentially, what his theory said was that the wind loads, and again, remember the Tacoma Narrows is a very windy place. Mr. Mellon's theory said that the wind load did not have to all be resisted by the roadway girders, but would be transferred to the cables. And so the roadway support girders did not have to be as structurally robust. And but there had never been a bridge built like this. So there was no experiential knowledge. It was just theoretical knowledge, if you will. And this is what Mr. Moiseyev, to a large degree, relied on, and it uh, was it turned out to be tragic. Uh, it another factor here with Moiseyev's design was that the traffic load at that point in history was projected to be very light and not much traffic. And so only two lanes of traffic were designed in Moiseyev's design. So not only is very shallow, but the roadway was narrow. And of course, that narrowness reduces the rigidity of the combined girders and roadway structure. And this is a table that illustrates the fact that the Tacoma Narrows Bridge was outside the envelope of experiential knowledge of bridge design at that time. And that's knowledge is still pretty much valid today. Um, some other bridges that had been or were going to be built. The George Washington Bridge, the center span was 3,500 feet. The girder depth was 36 feet. The Washington State proposal was for girders that would be 25 feet deep. The roadway width of the George Washington was 106. And the a key ratio of a couple of key ratios, the ratio of the girder depth to the length of the center span with the George Washington was 1 to 120. The ratio of the width to length of the center span, 1 to 33. The Golden Gate, which is in Northern California, near where I live, was completed in 37. The length of the center span, 4,200. Girder depth, 25 feet, exactly the same as proposed for the Tacoma Narrows Bridge by the state of Washington. Roadway width, 90 feet. Ratio of girder depth to length of center span, 1 to 168. Ratio of width to length of center span, 1 to 47. The Bronx Whitestone in New York was not built. It was kind of the evil twin, if you will. Excuse me, I was sneezing. It was kind of the evil twin of the Tacoma Narrows. Length of the center span, 2,300. Girder depth, only 11 feet. Width of the roadway, 74 feet. Ratio of girder depth to length of center span, 1 to 209. Width, length to length of center span, 1 to 31. And then the Tacoma Narrows Bridge. Length of center span, 2,800. Girder depth, only 8 feet. Width, 39 feet. So the ratio, these two key ratios, the ratio of the girder depth to the length of the center span, 1 to 350. Almost 3 times that of the George Washington Bridge. Ratio of the width to the length of the center span, 1 to 72, double that of the George Washington Bridge. Now, the Bronx Whitestone and the Tacoma Narrows were both built at approximately the same time, and very similar bridges. And the designers and operators of the Bronx Whitestone got a lesson in bridge design as a result of what happened with the Tacoma Narrows. And as a result, the Bronx Whitestone Bridge did not collapse because they were able to provide some remedial structural strengthening of the bridge. And the Bronx Whitestone is back there today, still working fine. So Tacoma Narrows, the federal government said, we'll put up the money, but you got to farm out the design to private firms. And so Moiseev and his associates undertook the design of the bridge. Construction began in September of 38. The bridge was completed and opened to traffic in July of 1940. Here's the bridge under construction. This gives you a picture of the very attractive bridge that was being constructed. The bridge was completed, another attractive photo, but notice the narrowness of the two-lane roadway, and another picture of the bridge before it collapsed. These are the guys that were doing the heavy lifting. And this was opening day for the bridge. And the program for the opening day's festivities. But the bridge became known for its movement immediately. Even while it was still under construction, even modest winds would cause the center span to visibly rise and fall over 4 to 5 second intervals. The flexibility was continuously experienced by the builders and workmen, who gave the bridge the nickname Galloping Gertie. Okay, now I think we're at the point where we need to take a 10-minute break, so let's do that. I've got 12:03. Well, I'm in California. I've got 3 minutes after the hour. And so let's come back at 10 minutes after the hour, and we'll resume here. So I'll see you all in about 7 minutes. Okay, this is Paul Geyer, and I'm back. So the bridge gets built, um, completed in 1940, and within about 6 months, it had collapsed. The state of Washington, of course, the engineers with the state of Washington, I'm sure they were saying, "I told you so." um, they hired uh, for the post-mortem on the collapse um, a professor at the University of Washington named Farquharson to investigate the collapse. And um, Farquharson had just started as a result of the oscillations that were observed uh, to put together some wind tunnel tests for the bridge. He didn't have time. Excuse me. He didn't have time to conduct any wind tunnel tests uh, before the bridge collapsed. But this is, I think, one of the positive things that came out of this tragic incident was that bridge engineers now almost routinely with large bridges conduct wind tunnel tests. And wind tunnel testing, of course, originated with airplanes, and the it has proven to be a an important step in the planning and design process for large bridges today. Um, Here is some of the high-tech equipment that Farquharson had available to him. A level and a probably 8mm movie camera. And these are some of Farquharson's notes during the studies that he undertook. Um, Different Band-Aid uh, 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 schemes were tried to control the oscillations, tie downs, and so on and so forth. Hydraulic buffers. And one of the goofier ones, but this apparently was a legitimate consideration. This is obviously a newspaper cartoon, but one of the proposals to control the oscillations was to drill big holes in the I-beam web so that the winds could pass through the but of course, if you did this, why what you're doing is substantially weakening the girders. So this was obviously a non-starter. Um, the Whitestone Bridge, I pointed out, is, as I characterize it, was the evil twin of the Tacoma Narrows Bridge. But the operators and designers of the Bronx Whitestone were able to learn from the uh, uh, from what had happened at Tacoma Narrows, and immediately were able to uh, uh, make improvements to the Bronx Whitestone, primarily increasing the depth of uh, uh, the roadway support girders in 1946. And again, the reason that this remedial work was not undertaken until 1946 was because there were great uh, constraints on the ability to acquire steel during World War II because it was needed for um, military purposes. And another uh, improvement was to provide streamlining fairings, which were added in 2004. And so although the Bronx Whitestone, as I say, was the evil twin, it's held up nicely apparently. So in November of 1940, the bridge had just been completed. Wind was blowing through the Narrows at a steady speed of about 42 miles an hour. That's those words, steady speed, are important. Um, and that'll become clear as we move along. At 10 in the morning, the bridge began to oscillate severely in the torsional mode rather than the transverse up and down type mode, which was had been observed previously. And here are some photos of the bridge beginning to oscillate in the torsional mode. Uh, One of the theories was that um, perhaps one or more of the suspender cables had broken, and you had an imbalance then between the two sides of the roadway and their girders. Um, the twisting motion, torsional, at its maximum, the sidewalk on one side was 28 feet higher than the sidewalk on the other side. And here is the bridge in its collapse. And the end result. Damaged cables, of course. And the thrashing about damaged the towers, piers. One of the fortunate things about this incident uh, was that this oscillation was observed um, early in the morning and had been observed previously over months. And when on this day, when the oscillations became particularly violent, there was time to close the bridge. And so there was no traffic on the bridge, and there were no fatalities or injuries as a result of this collapse. And that was fortunate. Um, Normally, I like to show a video um, of the actual collapse, uh, because again, one of uh, fortunate, you might say, things about it, everybody knew the bridge was going to collapse, and so there was plenty of time, uh, and a lot of people went out there with their 8mm cameras and filmed the collapse. And there are a number of these videos that are posted on YouTube. Uh, these are the URLs for three of them. And I normally like to show one of these videos so you can see the actual thrashing around that goes on. But because of the difficulties I've had today with this Zoom system, I'm not able to do that today. This is one of the videos, the starting screen. And as indicated, there were no fatalities uh, except for a little puppy dog that had to be on the bridge. And also there was a car that got stalled on the bridge, and the car went in the water, but the people got off. So um, now the investigation begins. Why did this happen? One early theory was that it was caused by resonance, but that pretty quickly got shot down because for resonance to be the cause of a failure like this, you have to have a forcing, uh, uh, something that is forcing the structure to oscillate, and like the wind. So if there were an oscillating wind, uh, and if it were oscillating right at the uh, resonant frequency of the bridge structure, which is a highly difficult thing to calculate, um, then resonance might have been a factor, but it was clearly documented that the wind was not oscillating when this happened. It was a steady 42-mile-an-hour wind, so there was no oscillation. So resonance failure uh, is not uh, a reasonable thing to conclude. Um, the let's see. Yeah, this is a discussion of the resonance theory. The federal uh, task force that was established to invest this included Theodore von Karman from Caltech, who's uh, has been through history one of the leading lights in aerodynamics, uh, primarily of airplanes, but uh, he was asked to serve as the chair of this task force, and it uh, he the resonance theory got pretty well discarded. Uh, but what quite possibly uh, might have been acting on the bridge was what has come to be called von Karman vortexes. If you put a blunt body in a wind stream, uh, the wind as it passes over the blunt body spins off behind uh, in kind of an oscillating mode like you see in this illustration. Um, this this occurs with wings on aircraft. One of the reasons on the latest generation of commercial airliners for those turned up wingtips is to mitigate the von Karman effect. So this was probably had something to do with why it on this windy day, why it was set into its oscillating mode. And there's more discussion here on these slides of this von Karman effect. And there's another phenomena called aeroelastic flutter, which essentially means kind of visualize it. If you take a piece of paper and hold it horizontally, or say a 1-inch strip of paper or a 2-inch strip of paper, hold it horizontally in front of you, and then let it go. As it falls to the ground, it flutters around, and that's just aeroelastic flutter, which is a which is a random fluttering. And the one of the things that was discussed was that perhaps the roadway deck was subjected to aeroelastic fluttering. Could be, maybe not. And so uh, the cause, what induced the oscillations was possibly the von Karman effect and then aeroelastic flutter. And there was a very well-known structural engineer, bridge engineer, Othmar Amon, was a member of the investigating commission. And he said that the Tacoma Narrows Bridge failure has given us invaluable information. It has shown that every new structure that projects into new fields of magnitude involves new problems for the solution of which either theory or practical experience an adequate guide. It is then we must rely largely on judgment, and if as a result errors or failures occur, we must accept them as a price for human progress. I don't really go along with that. I think you've got to recognize that um, if you do not have uh, a body of experiential knowledge of what works for the design of a bridge like this in a location like this, if you don't have that experiential knowledge, I think you have to proceed very, very carefully if you undertake to step outside the envelope of that experiential knowledge. Now, the ways that you can reasonably step outside, one is modeling, and that's what was touched on earlier, the wind tunnel testing of bridges, which has now become one of the tools that bridge engineers have to work with. So it's and another tool that you have to work with when you undertake to step outside the envelope of experiential knowledge is redundancy. I'm designing this building. My calculations show that I probably need 10 columns in this building. But quite frankly, I'm not really that sure. And there have never been any buildings designed in the past with 10 columns. So I'm going to apply some redundancy and throw in 2 or 3 more columns just to make up, to hopefully prevent a failure based on your lack of experiential knowledge. Hang on a sec. I want to check something here on me. Oh, okay. David asks, what type of stiffening was added to the Whitestone Bridge. David, get a copy, or maybe you will, as routine, get a copy of these uh, slides, because there is one back a ways that we did briefly look at that showed the stiffeners that were applied at the Bronx Whitestone. And it's a nice, neat kind of way to essentially increase the depth of the girders and to provide an open configuration so that the wind can go right through the girders. Um, so that's that's okay. Let's okay. So this is as I tried to point out right at the start, that there are in my view, two ethical issues that um, are raised by this incident. The first one is, don't compete for engineering work on the basis of cost or by telling the owner that you can do the work faster, cheaper, and so on and so forth. Because the design and construction process for even the most tiny project, the uh, undertaking of the design and the construction is a very organizationally complex undertaking. You've got all sorts of people running around on the job site or back in the design office. You've got people that are at the professional level, civil engineers, mechanical engineers, et cetera, et cetera. But you also, in the design office, you've got engineering techs, you've got what were called draftsmen back in the old days, and today I guess they're called CAD operators. And out in the field, you've got all kinds of trades running around. Um, a, a carpenter knows his business, carpentry, but he doesn't know anything about designing an air conditioning system or you know. So you simply cannot legitimately, ethically, in my view, compete for work on the basis of going to the owner and saying, "Oh, I can design it faster, cheaper, and deliver better value for you." Um, there are too many things that you, as an engineer, do not have control of. And in this case, this group of private engineers was relying on some theoretical stuff that had been put together by apparently an academic uh, individual in Austria. Might not have been in the academic community, but just a theory of how a suspension bridge could be uh, designed and constructed uh, more cheaply. And so that is I think, an an ethical issue that is raised here, and the answer is, don't compete for engineering projects on the basis of cost, or any of its different manifestations, faster, cheaper, better value, etc., because you do not control all of the things that are going on. Um, This also, I think, is a rather unfortunate turn of events historically in the engineering business here in the US, is that our friends in the construction end of things, because as is well known, they absolutely detest getting their jobs by competitive cost bidding. And so they now go to owners all the time, private companies and uh, public agencies. And they say, oh, we can do it faster, cheaper, better if you give us a design build contract, and we'll design the whole thing, and then we'll build it. And that's, of course, what the design build contractor does is he goes to 5 civil engineers and says, give me a price to do the civil engineering on this building, goes to 5 mechanical engineers and says, give me a price to uh, design the mechanical features of this building, and on and on and on. And as the end result is that the building is being designed by engineers who are under severe economic pressures, and what they will, being human, what they will do is come up with a design that is cheapest for them to produce. And that's not necessarily in the best interest of the owner. And so uh, the design, the currently extraordinarily popular uh, business called design build is, I think, not doing any favors for owners. But owners are pretty naive people, and that's just the way it goes. Um, okay, the difference between theoretical and experiential knowledge. The other uh, ethical issue, and it's kind of a combination ethical and um, technical, is uh, don't step outside of the envelope of experiential knowledge. Technical knowledge, just something that somebody thinks might work. Experiential knowledge, this is what's done in the past. It worked. The building didn't fall down. Let's do the same thing here. Um, okay, now let's see. I'm looking at my clock here. So let's get through. Pardon me. The earlier question about the retrofits at the Bronx Whitestone Bridge. This shows clearly what was done, and the bridge is working fine. Um, and let's modeling. Uh, I've talked about that already. Wind tunnel testing. This bridge, which is near me, where they did substantial wind tunnel testing. And now let's pause here. Let me get to the lessons learned. If the theoretical knowledge base underlying a design is weak or incomplete, it must be supplemented by an adequate base of experiential knowledge. And if the experiential knowledge is weak or incomplete, it must be expanded until it is adequate. A principal way of practically doing this is through appropriate modeling, perhaps computer modeling. In the example of the Tacoma Narrows Bridge, the modeling that might have prevented the collapse was wind tunnel model testing. Um, and in competing for engineering contracts, do not propose the designs that are not supported by an adequate and complete theoretical and or experiential knowledge base. Do not compete for engineering contracts by making claims that you can complete the project at a lower cost than your competitors, because you do not have control of all of those dozens and dozens or hundreds and hundreds of people running around on a job site. Okay, let's see if we've got some questions here. What type of Eugene says, did the Eastern engineers stay in business? Oh, I didn't, wasn't able to go to the morgue. No, but my understanding is that Moiseyev's career, he had been a very well-known and highly respected bridge engineer until this Tacoma Narrows Bridge incident occurred. And my understanding is that his career was uh, destroyed from that point forward. Now, Dave asks, was the truss added on top of the girders? And from that picture you just saw, yes, the truss at Bronx Whitestone was added on top of the girders. Well, and James says, when did safety factors come into play with design? Well, safety factors have and now are quite pervasive in engineering. Because we learned that theoretical knowledge is almost never going to be adequate to completely and safely design any kind of a structure or machine, et cetera, et cetera. And so you know, just like in the all of the building codes, you've got safety factors all over the place. And so my feeling is that safety factors did not come into play until building codes began to be the big factor that they are, which was kind of in the mid 20th century. So, but yeah, safety factors, you know, this book is designed for a safety factor of 5. I'm not really that confident I know what I'm doing. I'm going to use a safety factor of 7. Let's see, just here, and Brian says the original budget was 6.2 million. What was the engineering fee associated with the project? And was that included in the 6.2? I think that the engineering fees were included in the 6.2. Again, we're talking about 1930s style prices. So let's see, Thomas says you should review a presentation, project management lessons from the Tay Bridge disaster. I don't know what that bridge is, but that's a good heads up for me. I'll try to do that, see what I can come up with. Thomas says that was a railroad bridge that collapsed in 1879. Well, that's going back to an era when I'm, you know, really that involved in. Joe says, were any design codes changed or initiated as a result of this failure? Well, I haven't done a study of that, but I'm sure that they were created. Design codes were created uh, as a result of failure. Now, uh, an example that we see on the news, uh, I don't want to say nightly, but earthquakes in Turkey or Syria or places like this. And they don't have any building codes that are in full in any way, shape, or form. Um, I've been to Turkey, uh, driven through the countryside, and you see people out there building their mud brick houses, unreinforced, just one brick at a time. And this is an economic thing. These are very poor people, uh, and they just need a roof over their heads. But then when you get an earthquake, you see these hellacious uh, things that we've seen on TV not this many months ago. So all right, let's see. Let me get to the quiz here and just run through it real quickly. Uh, the Here, this was uh, the replacement bridge, and you notice also that it's 4 lanes instead of 2, and you see that the support girders are open web girders. All right, now let's run very, very quickly through the quiz here. It's not rocket science by any um, stretch of the imagination. Question 1, the Tacoma Narrows Bridge was of the blank type. That, of course, is D as in dog suspension. Question 2, the Washington Department of Highways proposed blank girders to support the roadway. And of course, that is C as in cap, steel truss girders. Moiseev proposed blank girders to support the roadway. And what he proposed was these steel solid I-beams, D as in dog. Number 4, the United States blank strongly supported construction of the bridge. That was best answer is A, is the military, because of the, again, the specter of World War II. The blank provided the majority of funding for the project, and that federal agency that controlled the purse strings was C as in cap, the Public Works Administration. 6, prior to the day of collapse, the oscillation of the bridge that had been observed the blank type, and that, of course, is transverse, just up and down, sinusoidal curve. Uh, 7, on the day of its collapse, the oscillation of the bridge that was observed was of the blank type, torsional, twist, 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 twist. And a pretty good guess of what had happened was that one or more of the suspension cables broke on one side, and there was an imbalance in the resisting force of the bridge. 7, no, I just did that one. Let's 8, blank was not one of the possible causes of the collapse identified by the Federal Works Agency in the initial investigation of the collapse. And that was, oh, I didn't mention this, but one of the theories that was thrown around was that the wave action of the water in some way had caused this oscillation of the bridge, and that was discarded pretty quickly. Some of the videos that are available on YouTube have some shots of what the water surface was like at the time of the collapse, and there were moderate little fluttery waves, but nothing. Uh, Number 9, in order to investigate the oscillation of the bridge that was observed during construction and after its completion, Professor Farquharson conducted wind tunnel tests on a blank scale model of the bridge. He did this after the bridge had collapsed, of course, and it was a 1 to 200 model that he fabricated. On November 7th at about 10 a.m., a blank vibration mode of the road bed was observed for the first time, and that, of course, is torsional, B as in boy. Twist, twist, twist. With regard to aeroelastic flutter, the wind speed that causes the beginning of the fluttering phenomena is called the blank velocity. That's C as in cat, the flutter velocity. Minor point, but possibly some interest. One of the suggestions, but not the only one, for the failure of the Tacoma Narrows Bridge was mechanical blank resonance. And that was pretty well discarded simply because the wind was a steady 42 miles an hour. It wasn't oscillating such that you could induce a failure by if the forcing function was at the resonant frequency. 13, resonance is when a structure oscillates at maximum amplitude at a certain frequency called the natural frequency of the structure. The phenomenon is described by the differential equation shown, where C is the blank and stiffness of the structure, and F and omega are the amplitude and the angular frequency of the exciting force. And the answer there, if you read the little write-up on resonance that's included on these slides, C is the damping coefficient. C is in cat. 14 under resonance technical comment. In the equation below, omega sub r is equal to k divided by m to the square root. Omega sub r is the blank of a structure, and that is the damping coefficient. No, pardon me. B as in boy. It's the resonant frequency, omega sub r, the resonant frequency. And 15, in the equation below, omega sub r is equal to k divided by m square root. K is the blank coefficient of a structure, and that's the damping coefficient. So that takes us to the any more questions? Let's see. There was one after six. No, that's from Hisham. So hopefully, I gave you a couple things to think about when you're undertaking to design a project. In engineering, don't compete for it's not the damping coefficient, it's the stiffness. So I hope this has given you a couple of things to think about as you approach projects, and that will hopefully keep you out of hot water. So thanks a lot for letting me chat with you, and have a nice rest of the day. Bye.